In this video we're going to talk about practices for picking components and designing traces that interface with them. Components all have parasitics, but they're especially pronounced at high frequency. Here I've drawn 3 resistors, 2 in surface mount packages and 1 in a through-hole package. I've also included a model for a high-frequency resistor. The silver triangles outlined in blue indicate solder connections. Current has to move farther from the ground plane as it moves through components, which introduces some inductance. Also, the pads which are often wider than the traces that connect them, introduce capacitance to lower layers. And solder can introduce lots of stray capacitance. Even worse, if solder isn't connected evenly across a component, then there can be constrictions of current that introduce inductance or contact resistance. Taken together, all of these effects suggest that smaller components have fewer parasitics. The inductive loops are smaller because the current doesn't have to move farther away from the surface. Less solder is used to connect them, and the contact pads are smaller, which reduces stray capacitance and also makes them easier to interface with narrow transmission lines. Small components are also more likely to be smaller than the wavelength of a signal, which makes it easier to model them in circuit analysis. And finally, small components are also easier to assemble for robots, not really for undergraduates, but that's okay. And they take up less board area, so many passive used in RF designs are in tiny, like 10 by 20 mil packages. In addition to being big, through-hole designs present some special hazards for through-hole components present some special hazards for RF designs. They're notorious sources of radiation and coupling because currents in through-hole components can be very far from the ground plane, and because the wires that poke through a circuit board can create reflections at really high frequencies. And finally, because the wire leads are often poorly controlled impedances that look like little transmission lines. The wire leads can be rich sources of radiation if you're unlucky in your layout. And also, by the way, this process of reflecting off of a short piece of transmission line, or a short piece of transmission line that you reflect off of, is referred to as a stub. Finally, through-hole components are simply bigger, which means that you need to consider them as sort of distributed elements at lower frequencies. So don't use through-hole components for RF designs. Connectors also matter a great deal in the design of RF systems. They're very common failure points because they are places where a signal passes from one transmission line to another, which can cause reflections. As a result, your efforts as a designer and the quality of assembly is really crucial for connectors. I've seen lots of designs fail because of connector mistakes. So connectors come in larger and smaller sizes, just like components. And small connectors like UFL are popular for some of the same reasons that small components are popular. However, SMA connectors are really the workhorse for lots of mid-gigahertz design and prototypes. Designers tend to switch to UFL for very compact designs, so like antenna mounts for cell phones and stuff like that, and to 3.5mm connectors for very high frequency designs. One design decision that you have to make with connectors, particularly SMA connectors, is whether the connector will launch from the side of the board or the top of the board, which are the 2 figures illustrated on this slide. Side launch connectors present a smoother transition from a wire to an onboard trace because the signal travels in a straight line. Vertical connectors force the signal to turn 90 degrees, which is a bigger deal here than with traces because of the many parasitics that are built into connectors. So as a result, side launch connectors are preferred when possible. That said, connector designers know their business, and if you follow the layout recommendations for a vertical connector closely, it'll usually result in a successful connection. And that's good because the number of side launch connectors on a board is limited by the perimeter, and it can also be very difficult to route from the middle of a board to the edge. So don't be afraid of a vertical connector when it's appropriate, but prefer side launches as a rule of thumb. One other wrinkle for assembling vertical connectors is that lots of them are through-hole, which means they can introduce stubs just like through-hole resistors. And further, the crucial solder joint that determines if the signal pin mates well with the onboard trace is hidden under the connector. Side launch connectors are also really sensitive to their solder job on the connector, but you can inspect that visually because it's just on top of the board. Finally, your transmission line is unlikely to be the same width as your components and pins, especially if they have extra pads for soldering purposes. which presents some challenges for routing. A step change in the width of a transmission line represents a sudden change in the line impedance, and that can cause reflections. Though with the caveat that if these step changes are sufficiently small, maybe they're electrically small compared to your signal. So tapers or expansion of lines to mate with pads and components are called landing patterns, and they're really important. You can usually get landing patterns from component designers, and especially I've had great results asking connector designers for landing patterns for different board stack-ups. They have been really obliging about it. Sometimes even assigning an application engineer directly to me to make a custom landing pattern. However, if you can't get a manufacturer to bother with you, which might be the case for manufacturers that make a huge volume, like passive manufacturers, then a 45-degree taper often does an okay job, especially if the pad dimensions aren't too far away from the line dimensions. That taper is a weird piece of metal, and you have the option of either trying to draw it every time you connect to a component or building it into the component footprint, and I usually do the latter. Finally, it's worth noting that the effectiveness of vias really depends on how they're laid out. You can introduce a lot of additional inductance into vias if you use a wire that runs out to them. And that can have really bad consequences. I've seen high inductance vias cause instability in amplifiers, for instance, because the ground wasn't stable. So in order to make very low impedance vias, you want to connect them directly to pads, or move them directly onto the pad. I usually opt for connecting directly to the pads on the side like this, because sometimes putting the via in the middle of a pad violates design rules. It can create some weird heat sinking and solder flow properties. So in summary, small components have fewer parasitics than big ones, and small components especially have fewer parasitics than through holes. Side launch connectors often perform better than vertical connectors, especially through-hole vertical connectors. Landing patterns are really crucial for performance, so make sure you get them from manufacturers or fall back on 45-degree tapers. And low impedance vias won't be connected by traces, they'll just be merged directly into pads.